let's continue. Okay, let's now consider some useful identities. What this identity mean is that this is just a identity between single qubit circuits, and this means that just application of H, XH is the same thing as application of Z, a Pauli Z operator. And this H is the Hadamard operator, I recall. And similarly, if we apply HZH in order, that way, this is the same thing as application of X. And I also just want to show you how it is possible to transform identities to another identities. So just a moment. Now, since we have this first identity, we can multiply it by on both sides both sides by H here and H here. This means that we can multiply similarly by H here and H here. But H squared is a H squared is identity. So we can just these two operations annihilate, and these two operations also annihilate. And so what is left is here is that HZH equals to X, just this identity. So we can actually transform identities to another identities. Now, another useful identity is the following. We can express C0 operation with the help of control Z and H Hadamard gates. And again, we can use this same identity to prove this identity. So it is similar identity. And in total, what we have is that controlled NOT operation can be expressed with the reversed controlled operation and the applications of Hadamard gates. We also can, again, by what I explained before, we can transform this identity to this identity. So we can also express controlled Z operation with the help of controlled NOT and H Hadamard gates that act on the target qubit here. Some other useful identity is the following. So what we have here is a single qubit unitary, which is identity matrix times some global phase. Now, without the control, the action of this unitary is undetectable. So we may think that nothing happens. But if we write down this 2-qubit gate by the rules I previously defined, then it will be detectable. So this operation is not trivial. And in fact, it can be proved that it is easy to show that this matrix actually equals to this 4-qubit matrix. And here we have only there is no action on this qubit, and on the first qubit, it is this unitary single qubit unitary action happens here. If we have the controlled version of the product of two unitaries, then it is the same as the product of the controlled versions. And again, I recall that mathematically we write the product of operators in a different way than we depict them on the circuits. So the product here is different simply because a different convention. If we have the controlled version of tensor product of two operators, suppose, for example, U1 acts on this second qubit and U2 acts on this third qubit, and we control it, then it is the same thing as two operations. The controlled version of U1 just on this second qubit and the controlled version of U2 on this qubit. And the order actually doesn't matter, because we clearly see where this unitary acts on what qubit. Okay. Some more involved identity. What we have on the left is the the controlled version of this single qubit unitary. And suppose we can express this unitary single qubit unitary in this form. So here X are Pauli, just Pauli X matrices, and A, B, and C are some one qubit matrices with the condition that the product of them is identity, the trivial. Then if these two equalities hold, then this matrix and this gate actually equals to this sequence of gates. And we can we can write it for any single unitary U. So it is possible to find this decomposition for any U. To do it, what we need to express this unitary U by writing it in this form. So as was mentioned earlier by Andrei, that we can express any single qubit unitary as a product of three rotations over z-axis, y-axis, and z-axis again, but by some three angles. And then when we found this decomposition, we simply can take these operators A, B, and C by these formulas. So, and then these two identities will hold. Now, why this identity is important? It follows that the controlled version of some single qubit unitary gate is a combination of two C0 gates and four single qubit gates in general. So this circuit looks harder, but it actually contains simpler elements. So just C0 gates and one qubit gates. So we can say that it is conceptually simpler because the elements are simpler, and this element is harder. Another useful identity is the following. We can, for any one qubit gate V, we can rewrite this two controlled unitary as this set of gates. So, and this can be done for any V, where this is the adjoint matrix. And again, you may see that this circuit looks harder, but in fact, it has simpler elements. So here we have two controlled operations, and here we have only one controlled operations. And moreover, we can further expand this one controlled gates as by this identity. So in total, we have that any two controlled gate is also a combination just of C0 and 1 qubit gates. Now, using this identity, in particular, we can realize the CC0 gate if we simply take V as the square root of X. And this is this operator. This is a rotation by over X by P0, P over 2. And so also there are other possible ways to represent the CC0 simpler in a simple combination of C0 and some 1 qubit gates. Now, what we have, what if we have a situation with multiply controlled gate? Now, a multiply controlled gate can be realized as some sequence of two controlled gates with the help of some additional so-called ancillary qubits. For example, look at this situation. What we have here, the first 5 qubits are the control qubits, and the last qubit is the target qubit where the action of unitary single qubit unitary U happens. To express this operation, we add four additional qubits. Some we can call it them work qubits. And then one can show that this operation, unitary operation, actually equals to this sequence of operations. And as we can see here, in this circuit, there are only two controlled operations, only CC0 gates, sequence of CC0 gates, and a singly controlled U. And again, we can use the previous results to conclude that multiply controlled operations can be expressed as a combination of C0, usual C0 gates and the single qubit gates. Well, this is what I just said, that we can express them as a combination of C0 and 1 qubit gates. And there is actually a major result in quantum computing that it states that any n qubit gate, unitary gate, can be decomposed into a sequence of C0 and 1 qubit gates. I will not describe how it is done. You can, for example, find it in Nielsen and Chung book on quantum computing. And so C0 and 1 qubit gates form so-called universal gate sets. So it is why it is so important. It means that in practice, we can only realize in hardware only this type of gates to simulate any other gate. So it is very useful mathematical result. And also, I don't recall if Andrei mentioned it, but we can use the gates H and T to approximate any 1 qubit gate by taking combinations of them. And thus, it follows that the set of these 3 gates, C0, H, and T, is approximately universal. We can approximate with combinations of them any unitary gate on n qubits. Now, this theorem gives a decomposition, but this decomposition is not efficient in general. In general, it requires the exponential number of elements of this CNOT and 1-qubit gates. And this is something, and in general, this is not very useful. What we want in practice is to find the compositions that are efficient. So they contain only some polynomial number of gates, of simple gates. And finding such efficient decompositions is actually one of the most important problems in quantum computing, and it's also one of the hardest. And it is actually the state of the art in this science to find efficient decompositions. Okay, now let's see an example of a circuit, and this is an example of a quantum teleportation circuit. Now, what is quantum teleportation? In quantum teleportation scenario, we have two parties. It's Alice and Bob. And you may think that Alice and Bob are separated in space. So suppose Alice on one planet and Bob on the other planet. And they want to be able to teleport some quantum state from Alice to Bob. So what they will do at first stage, now this is time flows in this direction. At the first stage, now we have 3 qubits here. Now before any teleportation happens, you may think that there is a preparation happens. Now in the preparation stage, here we have, you may think that this first qubit is not even exist yet. We have these 2 second and third qubit in the ket 0 states, and we entangle them by this operation. And it was mentioned by Andrei that it actually produces the Bell state. It entangles these 2 states, and the result will be the Bell state on these 2 qubits. And it can be performed by some third party on some third planet. It doesn't matter. And then after we entangled these 2 qubits, this third party sent the second qubit to the Alice planet, and the third qubit, this third party sent to the Bob planet. So at this point, this second and third qubit are separated in space. Now, and this is the first stage. And the second stage, Alice receives the first qubit that she wants to teleport to Bob. And you may think that, for example, you may think that the first qubit is also at the Alice location. So Alice in the possession of the first qubit and the second qubit at this point in time. So then she also entangles them with this operation. So she entangles her 2 qubits, the first and the second one. But since the third and the the second and the third qubits were already entangled, in fact, all 3 of them will be entangled at this point. And now, after this operation, she performs measurement of the first on this first qubit and this second qubit. Then the measurement will be some bit, because the measurement will result in either 1 or 0, and here also 1 bit which is either 1 or 0. And then she sent these classical bits to Bob. by some classical means. And the final stage, when Bob receives these two classical bits, he performs the classically controlled operations. So he apply x to its qubit if the result of the measurement here was 1, and do nothing here if the result was 0. And it applies operation z here if the result of the measurement here was 1, and also does nothing here if the result was 0. And in fact, the end result of all this circuit will be such that the state of this third qubit will be disentangled with this two, and it will be exactly in this state as was here. And so that's why we call it teleportation. So we first note that there is no actually transfer of physical qubits. So only the state is teleported. Only this, you may think that these coefficients. And also note that Alice and Bob don't even have to know what this state was. So they don't know these coefficients alpha, and they absolutely have no knowledge about the state. So they can blindly pass somewhere further this state. For example, teleport it further, or Bob can physically move this qubit with the state somewhere else. Now, why this circuit works? Why this is true? Now, there are many books and resources that explain quantum teleportation. Well, mostly by simply calculating all the mass, but I want to show some a little bit unconventional way how to prove that this scheme works. I will use the principle of deferred measurement that I talked before. By this principle, this classically controlled operation can be substituted by this operation. So at first we apply a quantum controlled version of X gate, and then measure, and again, and we apply this quantum controlled operation, and then measure. So this is an equivalent circuit. Okay, now let's next we use the following circuit identity. In fact, this inner part, this inner gate, 3-qubit gate, this is some 3-qubit gate. So this is actually a matrix of size 8 by 8. It equals to this circuit, to this gate, and you can verify it. You can check it simply by computing this matrix, 8 by 8 matrix, and this matrix, and you can see that you could see that those matrices are exactly the same, and so the actions will be exactly the same. Now, what we do, how to prove the result. Okay, just a moment. Now, since the input state was psi ket 0 ket 0, then it was this state psi here, 0 here, and 0 here, right? Now, can you see what I draw right now? Can someone tell me? Okay, I hope You can see this. Now, this is a swap operation. So after the swap, what we will have here is the ket0, ket0, and ket psi. Now, since we have ket0 here, and it is disentangled, then this operation will have no effect. And similarly here, this operation will have no effect because we have exactly zero state here. So we can ignore these two operations. And in the end, it will be the action of H. So in the end, what we will have here is just plus, plus, and psi state. So we can just, this identity help us to deduce that in the end of this circuit before measurements, there will be plus state here, plus state here, and the psi state here. And so this proves that this the state of this qubit will be disentangled, and it will be exactly psi. And it also shows that the measurement will result in some equal probabilities of ones and zeros. Okay. And finally, okay, I see some questions. Is it possible to share classical quantities such as forces, energies into a quantum circuit based on these principles? No, classical quantities can be encoded by some quantum states, but we can inject them directly. So everything classical must be somehow encoded as a quantum state by some very classical things. So this is something special here. Now, finally, I want to talk about relation to classical computing. Suppose we have an n qubits and a unitary U permutes the standard basis of this n qubits. So each vector of this like this equals to some basis vector. Now this means that this unitary U is corresponds to some permutation P that acts on the set of binary sequences of size n, binary strings of size n. And there are there is actually a huge number of possible permutations because the total number of strings is 2 power n, and we have that there are 2 power n factorial permutations. Now, vice versa, if we have some permutation on this set of n-bit strings, then there exists a unitary that permutes the standard basis accordingly. So we can just define some unitary that corresponds to this permutation P. Now, for example, CC not gate that I mentioned before corresponds to the permutation of 3-bit strings, right? So this permutation actually mostly trivial, but only here we have this permutation of these two strings. Now, without relation to quantum computing, we call this operation on bit strings a classical CC0 gate or a classical Toffoli gate. So this function that acts on this set of 3-bit strings. Okay, but in classical case, we can consider any function. So any function, we can define any function from n-bit strings to m-bit strings, right? So for example, the usual end function is from 2 bits to 1 bit and defined by this rule, right? So if it is 0 unless these 2 bits are 1, and then it's 1. So it is so we have a problem here because the permutations are reversible functions, but the general functions f are not reversible. And actually, if a general function f of such function f is reversible, it is necessary a permutation. So it is the n must be equal m, and it must be a permutation necessarily. So it seems there is a problem here. We can't simply represent end function as some unitary operation. We can't encode this end function directly. But nevertheless, there is a way to canonically extend any irreversible function to a reversible one. What we do is the following. Okay, suppose there is some function f from n-bit strings to m-bit strings. We define the function p of f that acts on a Cartesian product of these two sets. Now, this means this set is actually isomorphic to just n plus m bit strings, and it acts on the same the image of this set is the same set. So it acts on the same set. We define this p of f function by the following rule. So here x is the n-bit string, y is m-bit string, and on the action on x and y is the following. So we take here the bitwise XOR of y and f of x. So XOR is just, you may think, just sum by sum of bits by modulus 2. Now, clearly, if we take y to be just a string of zeros, then the result of this function will be just x and f of x. So this explains why we call it an extension. So we can see, if we have access to this function, we can simply compute f of x if we want, just by putting these arguments as inputs. Now we also have the following. If we consider the composition of p of f and p of f and compute what it does, right? We can compute it, simply rewrite by this rule, and we will have this formula here, and this is actually annihilates, and the result will be again x and y. So the composition of p of f and p of f is actually an identical function. And this means that p of f has an inverse and it equals to the p of f. This means that p of f is a reversible function. And thus, it is a permutation on n plus m bit strings. And this allows us to define the corresponding unitary action. So we just this simply defined it in accordance to this P of f. So we can write it, for example, we can write it by the following formula. Just U of f acts on two registers of qubit of size n and m, and the result will be this state. This is actually a basis state on the set of n plus m qubits. Okay, now you can check that if you take the classical n function, its canonical extension actually will be the classical CC0 gate, classical Toffoli gate. And so we can, and this gate corresponds exactly to the quantum CC0 gate. And so in this way, we can encode this n function as a quantum, as this quantum gate. Now, in general, if we have any classical circuit, then, classical circuits, I recall, they contain these gates that are not reversible. But by using this principle, as I explained before, we can transform the non-reversible gates to reversible gates, like here. So we transform AND to the CC0 gate. And in fact, we can do it for every gate in the circuit. So we can transform non-reversible circuits with non-reversible gates to reversible circuits with reversible gates. And in fact, there are ways to do it with comparable complexity. So the number of gates will be of, let's say, comparable size. Just for a moment. And when we have a reversible circuit with reversible gates, it just directly corresponds to a quantum circuit. So just like here. Now this means that the complexity. What this means is that the complexity of any classical function can't be significantly smaller than the complexity of the corresponding quantum circuits that realize this corresponding unitary U of f on n plus m qubits. And in other words, this means that quantum computing is not less powerful than classical. And in many cases, it's actually much more powerful. It is exponentially more powerful. And I hope next speakers will give you some examples of it. And this is all I wanted to say. So I think we have time here, but if there are any questions, I will be glad to ask, to answer.
Okay, yes, there is a question.
Okay. Therefore, there cannot be classical cloning function. No, there is no. You think the problem is where we talk about correspondence with classical functions. Now, in classical world, we know the states that we clone, right? You can't clone something that you don't know, that you don't see, right? And the essence of this no cloning theorem that I mentioned before is that we can't clone something that we don't know, right? If we know the state, a quantum state exactly, if we know what we want to clone, that of course we simply can generate it. So there is no problem to make copies, the quantum copies of something that we know exactly. So this is a difference here. So it is about cloning of something unknown but physically present. And I hope this answers the question.
Another question.
Can you explain once again how we got the swap gate in the quantum teleportation example? Okay. Yes. Now here it is this identity. Just remove everything here to better see it. Now this on the left, it is some unitary action, unitary gate. So this is simply a matrix 8 by 8. And on the right, there is also a matrix of the also some unitary gate that acts on 3 qubits. This is also a matrix of size 8 by 8. You simply can compute these matrices by the rules that I showed before. Simply, those are actual matrices, and you can, if you compute them, you can check that they are the same. They're the same matrices, and that's simply it. So there are other decompositions. So there are many different ways to represent a matrix, a unitary gate as a sequence of qubits. But this representations is useful to prove that teleportation works. Simply as simple as that. I hope this answers.
Okay, there are no questions. Thank you very much for your lecture, and also thanks to all visitors for your attention. Tomorrow we will start with Introduction to Quantum Algorithms by Marco Rodelli from Trinity College Dublin. And I think for today it's over. See you tomorrow.
Yeah, thank you for attention. Thank you for.
Yeah.
Have a great day.